We have a collision where one car rear ends another car. I've got car 1, that's the car that is doing the driving. Car 2 is the one that's parked. And then they hit and slide off together at some speed, a distance of 24 meters. What we're looking for is how fast that blue car was going at the time of the actual accident. Now, while I have the cars numbered 1 and 2, I'm going to refer to them as the blue car and the pink car from now on. Unless you have some colored pencils, you might want to put some subscripts next to any blue variables that say M1 or V1, and then for anything pink, M2 and V2. But for now, I'm just going to stick with blue and pink since we have the color coding. Now, this is a collision, so we know that conservation of momentum will be applying. So I'm going to start there. I'm going to say, all right, the momentum of the blue car plus the momentum of the pink car has to equal the momentum of the blue car prime plus the momentum of the pink car prime. And I can expand those and put in the M and the V for each one. Before I do that, though, just to make my life a little bit easier, I know that car 2, or the pink car, was not moving. It was parked at the beginning of this problem, so it's not going to have any momentum. So I can cross that out and make our algebra a little bit easier. So now I know that's mass of the blue car times velocity of the blue car, which is what I want, equals mass of the blue car times the velocity prime plus mass of the pink car times velocity prime. Now I wrote both of those velocity primes in purple because they both move off together. They're moving at the exact same speed, so that is the exact same value. So it's the same variable. So instead of making it blue or pink, I just put it somewhere in the middle, made it purple. All right, now, normally we would just try and solve for this initial velocity of the blue car right away, but I don't have all of the variables. I don't know what they are. I know the masses, but I don't know that velocity after the collision. In order to find that, I'm going to have to use the distance that they slid and the coefficient of friction. Here's how I can do that. I can use conservation of energy, and I know initially those two cars, when they collide, they're going to have kinetic energy. So I can go with total kinetic energy 1. And I'll just put those two masses together as 1 when we solve for this. And all that energy is going to go away. That energy is going to go away as a result of thermal energy or friction. Now if I expand that equation, I get 1/2. I'll put mass of the pink car plus the mass of the blue car there, because they're moving off as one thing after the collision. And that's times v squared, and that's v prime, because v prime is how fast they're moving right after the collision. And this conservation of energy equation is from the moment they collide till they slide 24 meters and eventually stop. And I know that thermal energy is equal to the force of friction times the distance they slid, d. And you might say this doesn't really help us a whole lot because I don't have the force of friction, but we actually can get it, and we can get it pretty easily, and here's how we do it. On the left side, I still have the 1/2 times those two masses added up, times v prime squared. And force of friction is the coefficient of friction, so I'll write that down, mu, times the normal force. Now we learned when we were doing forces that when you have two objects, there's no forces pulling up at any kind of angles or anything, that the force of gravity down is going to equal the normal force up, and that's what's happening here. And the force of gravity being equal to the normal force, we know that that means that mass times 9.8 is equal to the normal force. Now the mass would be the mass of both of these cars together. So that's what I'm going to write in here. For mg, I'm going to have the mass of the pink car plus the mass of the blue car. That's going to be multiplied by g, which is 9.8, and I can't forget to write the d there. That didn't go anyplace. Now what happens is the masses actually cancel out. I can divide both sides by those two masses, and they will go away. Just cancel them out right there, and what I'm left with is a much easier equation, which is 1/2 times the velocity of those two cars after they collided squared equals the coefficient times gravity, which is 9.8, times the distance, which we were told is 24. So now I can solve for how fast these cars were going right after they collided, and the reason I would want that is, again, once I solve it, I can plug right up here into my conservation of momentum equation and solve for what I'm really looking for. So let's finish this up. I'm going to divide the 1/2 to the other side. It's like multiplying by 2. So on my right side, I have 2 times mu times g times d. And I want to get rid of that squared, so I take the square root of all of that stuff. So when I do that, my velocity prime is going to be, let me write out all the numbers. I've got 2 times 0.8 times 9.8 meters per second squared times 24 meters. Now I am just about out of room here on the bottom, but when I plug into my calculator 2 times 0.8 times 9.8 times 24, I get that the speed, v prime, that they slide off together with is 19.4 meters per second. Now I can take that number, use it up here in my conservation of momentum, and get my actual final answer. Again, I'm looking for the velocity of the blue car right before they collide, so I'm just going to divide my mass to the right side. And this is a long one. This is what that gets me. On the left side, I'd have velocity equals mv prime plus pink m v prime all over the mass of the blue car. Plugging in my numbers. See if I have room for this. 430 kilograms times 19.4 meters per second plus 350 kilograms times 19.4. Sorry, I just went into the blue a little bit there. It might be tough to see. And we're going to divide that by 430 kilograms. Now, there's a lot of writing on this one. And when we finish this all up, what we see is that the speed of the blue car right before the collision, how fast was it going? It was going 35.2 meters per second. So just quick review, wrote down all of our stuff, started with conservation of momentum, knew that we were missing some variables, had to solve for the speed after the collision. I used energy to get that. All the kinetic after the collision equaled the thermal that was gone due to friction. Solved for that velocity prime and was able to plug that back in and get 35.2 meters per second.